Hello everyone, my name is Darshan Batavia and currently I am doing my PhD under Professor Kropatsch in Technical University Vienna. In this presentation titled Image Equals Structure plus Few Colors, we will dive deep into how a hierarchical approach can be used to precisely represent an image with its structure dominated by critical points and their respective colors. This research was conducted in collaboration with Professor Rocio Gonzalez-Diaz from University of Seville and Professor Kropatsch from Technical University Vienna. This slide explains the crux of the paper. On the left image, you can see a 4-neighborhood region adjacency graph where every pixel is represented by a vertex. The pixel intensity serves as the vertex attribute while the contrast serves as the edge attribute. On the right side, we can see a graph which contains a high-level structural information of the image. With the help of combinatorial maps as the data structure, we can very well construct an irregular image pyramid to achieve a reduced graph like one on the right side and reconstruct back the original image. Since the critical points, namely the local maximum, the local minimum and the saddle points dominate the structure and the topology of the image, the graph of the critical points can very well be used to capture the image structure. Now let us start with the basics and definitions. This slide shows a digital image on the left and a 2.5 dimensional geographical terrain model on the right where the height of the terrain corresponds to the pixel intensity. Analysis of such terrain models was first done by Maxwell in 1870. The terrain models will be often showed throughout the presentations for better visualization. All the points on the digital image and the terrain model can easily be categorized into critical and non-critical points with help of the local binary patterns. On the left, we can see a peak with a red dot which depicts a local maximum. The graph below with a vertex marked with a plus sign corresponds to the red dot and the edges are oriented from higher intensity value to the lower intensity value. Therefore, the edges are oriented in the outward direction. In contrast, we can see a local minimum represented by a yellow dot, where all the edges are oriented in an inward direction. In the third column, the green dot represents a saddle point. The vertex is marked with a cross sign which has two opposite edges in outward direction and two opposite edges in the inward direction. The last image on the right shows a slope point in blue color. All the remaining configurations of edge orientations apart from the critical points are considered to be the slope points or non-critical points. The interesting part is if we traverse the edges in the clockwise or in an anti-clockwise direction, then the local maximum and the local minimum have zero switches since all the edges are oriented in a single direction, while the saddle have 4 or more number of switches in orientations and slope vertex have exactly 2 switches in the orientation. In this way, we can classify the vertices based on the edge orientations even for a higher degree vertex. After classifying zero-dimensional points, we move ahead to classify one-dimensional curves. In the image, we can see a curve connecting 2 points, a maximum and a minimum. It is named as a monotonic path since all the oriented edges on the monotonic path are in the same direction. In case if the contrast is 0, the edge remains unoriented and a curve with unoriented edges is called as a level curve. A level curve shown in a yellow color can be a part of a monotonic path as shown in the figure. Note that a path connecting two critical points is always a monotonic path, and all the pixel intensity values on the path are within the range of the corresponding two critical points. In this example, all the pixels lying on the path connecting the local maximum and the local minimum have the gray values between the corresponding maximum and the minimum, and in this exact way, the critical points dominate the structure. Let us move ahead in understanding the algorithm. The algorithm is named as Topology Preserving Irregular Image Pyramid, in short TIIP. It is a bottom-up approach as shown in the image. The second step is to insert the hidden saddles. If the sampling frequency is lower than the Nyquist criteria, then there is a possibility that the saddle points are not captured. All such configurations of pixels are termed as non-well composed picture. By inserting hidden saddles, we convert all such non-well composed configurations into a well composed configuration. After this step, all the critical points are present in the region adjacency graph. Now we figure out the details about reducing the size of the graph. On the top image, we see a region adjacency graph with few edges marked in green color selected for contraction. A set of such edges is called contraction kernel, and we use a well-defined graph operation called edge contraction to merge the two corresponding vertices connected by the contraction kernel. The lower image shows the graph after the contraction operation. Next is the edge removal operation. The edges which are redundant and which do not contribute to the image topology are considered as removal kernel. The image at the top shows the edges marked in green color which can be removed without disturbing the structure of the image. The image below shows the graph after the removal operation. After consequently performing the contraction and the removal operation, we get a reduced graph. The stack of such reduced graphs form an irregular image pyramid. The irregular pyramid can very well be used for studying the topological and structural properties of an image. The space between such critical points is defined as the slope region. More formally, a slope region is defined as a region where all the pair of the points can be connected by a non-unique monotonic path as shown in the image. A slope region promises that there are at most one local maximum and at most one local minimum inside a slope region, while the saddle exists only on the boundaries of the slope region. This properties of slope region restricts the number of critical points and optimizes the connection between them, helping us to preserve the topology. Through our proposed algorithm, we divide an image into slope regions. In other words, a combination of slope regions are used to depict the structure of an image. Besides this, computationally speaking, a slope region is just a collection of two critical points, a maximum and a local minimum, and the connections between them. Further details are explained in the paper partitioning 2D images into prototype of slope regions. For experimental setup, we implemented our algorithm on the Berkeley segmentation dataset PSD100, where the top level of the image pyramid consisted of approximately 33% of the vertices as compared to the base level. We compared our algorithm with image super resolution algorithm, where practically first the image is reduced through a regular pyramid method and then are attempted to increase the resolution. Though the applications are different and it is not a fair comparison, the visual quality of the reconstructed images show the advantage of irregular pyramids over regular pyramids. For objective quality assessment, we used SSIM and FSIM for structural and feature similarity, while signal to noise ratio to capture the global quality of the image. On the left, we can see the original image, and on the right, we can see the image with approximately 33% of the colors. The zoomed image on the bottom shows how well the fine details and hair-like details of the image are preserved, which are usually lost in regular image pyramid. Similarly, for this image, the fine details of the fence and its shadow are captured, which are considered to be an important texture content in a lot of medical applications, for example, detecting hairline fractures. There is a space for improvements. The algorithm do not work extremely well in smooth regions where the contrast is not significant and the part of the images which are not in focus. Here are some objective results where the irregular pyramid method TIIP outperforms the regular pyramid super resolution methods. To conclude, the proposed TIIP algorithm represents an image as a combination of graph of critical points and the color of the corresponding critical points. It preserves the fine details and the high frequency texture information of the images. The hierarchical approach provides a multi-resolution structural information of the image. Use of combinatorial maps as the data structure permits the parallel processing to further reduce the computational time. The parallel algorithmic complexity for building the pyramid is in the order of log of d, where d is the diameter of the largest object. For future work, we are already implementing a GPU version of the algorithm which requires less than a minute to compute the whole pyramid for an image. Though this time can be considerably reduced by eliminating the unwanted steps for a specific application. Further, we can use machine learning approach to determine the contraction kernel. Knowing the fact that the contraction kernel dominates the construction of the pyramids, using machine learning to determine the most optimized contraction kernel will help the algorithm to derive application-specific constraints to achieve better results for several image processing applications like connected component labeling or image segmentation and object detection, etc. If you have any further questions, feel free to contact me.